Welcome. Here we'll take a look at all the symbols that we need as we learn how to estimate unknown population parameters by looking at our observed sample statistics. So we'll start with learning how to estimate a population mean. So if we are unable to gather data from an entire population, but we'd like to know the population mean, then our best estimate for it is the corresponding sample mean, X bar. And after we learn how to estimate means, we'll actually be moving to estimating proportions, like what percentage of consumers think Chester makes the best churros. So population proportion. So this will be P. And we saw that in chapter 5, actually, when we learned the binomial distribution. So P will be our population proportion. And if we're unable to access an entire population, the sample proportion is P with a caret on top, that caret symbol, and that is read P hat. So if I surveyed 20 consumers and asked how many of them think Chester makes the best churros, the percentage that say, yes, I think Chester's are the best, that would be your P hat. So we'll get to that in a future section. And then we'll also learn how to estimate sigma. So we've been given sigma frequently in chapter 6, and now we'll learn how to estimate that in this chapter. And the best point estimate will be the sample standard deviation. And then variance we don't do often in this class, but that would be sigma squared for population, and then S squared for sample variance. So it's going to be really important that we have our symbols down. So I'm repeating myself a little bit here. Population mean is mu, sample mean is X bar. And then we really have to be cautious here when we see standard deviation. We're very used to writing sigma every time, but now we need to be careful of population standard deviation sigma, but sample standard deviation is S. And the difference here is going to play a role in how we estimate our mean. All right, but first what we'll do is just take a look at writing these confidence intervals for a mean in two different forms. So as we learn to estimate a mean, a confidence interval is always symmetric about its point estimate. So our point estimate X bar will be in the center of the interval. And then we just call these just abbreviated lower limit, upper limit. And then the distance from the point estimate to the lower limit is our margin of error. And as well, from our point estimate up to our upper limit, that distance is the margin of error. So if I took a look at the width of the entire interval, so from lower limit to upper limit, I would have 1e plus 1e. So that entire length would be 2e. We'll see that coming up as we look at some formulas. All right, so let's look at this example. Based on a random sample of 200 American families of 2, a researcher estimates with 90% confidence that the true population mean, so always good to recognize what it is we're estimating. So they believe that mu, the population mean spent on groceries per week for all American families of 2 is between $82 and $90. So based on the 200 families they surveyed, they believe that for all American families, that the value is between those two numbers. All right, so because they said between, the form they're giving us is our lower limit, 82, less than the parameter we're estimating right now is mu, and then the upper limit of 90. Okay, and what we'll do is look at changing it to the other form. So because intervals about to estimate means are symmetric, we can take a look at them in two different ways. So let me just graph this first. So lower limit here, 82, upper limit 90. So we think the mean is somewhere between those values. So in order to convert it to the other form, we're interested in what was the point estimate and what was the margin of error. So because the point estimate is always in the center of the confidence interval, and actually because this one has such nice numbers, I can see the answer 86 there in the middle. But in order to find it mathematically, we can just average the lower limit and upper limit. So if I take 82 and add 90 and divide that by 2, so 82 plus 90 is 172, divide by 2, so $86. So that's our point estimate. So point estimates are single values there. And then to turn that into a confidence interval estimate, we include the margin of error. And one way to find it here is to recognize that lower limit to upper limit, this whole length is 2e. So if we found the length of the interval and divided it by 2, we'd have our margin of error. So I'll take it that way. So 90 minus 82, upper minus lower, divide by 2. That will be 8 divided by 2, or 4. And we could have seen that actually another way, but let me just label this. So that distance is 4, as well as that distance is 4. All right, so these formulas always work, but notice that because the sample mean I found to be 86, another way to get 4 would just be to look at that distance. So 90 minus 86 is indeed 4. All right, so that form of the confidence interval, we're just giving our point estimate, so $86. I'll put units in the sentence in a moment, but that's $86 plus or minus $4. All right, so second way they could have released the findings of this study is to say based on a sample of 200 families, a researcher estimates with 90% confidence that the true mean amount spent on groceries per week for all American families of 2 is, so instead of saying between, we're saying we think it is. So our point estimate, which was $86, accurate to within. And when we see that phrase within, we're talking about our margin of error. So accurate to within $4. And because it says within, we don't have to say plus or minus, but you're always welcome to do that just for emphasis that we're talking about our margin of error. All right, let's see if we can go the other direction. So if you're given this form, how do we get back to the other form? All right, so a new example though. So let's take a look at number 2. Okay, so based on a random sample of 90 trees in a large apple orchard, the owner estimates with 95% confidence that the mean number of apples per tree for the population of trees in the orchard is 525, accurate to within 10 apples. Okay, so the is 525, that's their sample mean. And again, looking at that word within, that indicates your margin of error. So this time the given form is the point estimate and then plus or minus the margin of error. All right, so on my graph here, there's the X bar, 525. And now we will convert it to the form with the limits. All right, so all we have to do is take our 525 and subtract our margin of error to get the lower limit. That will bring me down to 515. And then take the 525 plus 10, and that will bring me up to 535 as my upper limit. And we'll again be able to see the symmetry here. And I'm just going to go back and label the margin of error so we can see we did it correctly here. So 525 to 535, that is 10. And then 525 down to 515, that is 10. All right, so we could either say 525 plus or minus 10, or the lower limit, 515, less than mu. So remember, it's mu that we're estimating. So we think the population mean is between 515 and 535. So we really want to be careful with symbols. When we create the interval, it's based on X bar. So this was the sample mean. We're not estimating X bar. We know X bar for certain because we collected a sample. This symbol mu is the parameter that's being estimated. So the confidence interval is the estimate for mu. And now I can say, based on these 90 trees, that this owner estimates with 95% confidence that the true mean number of apples per tree is between. So when we say between, we want lower limit, upper limit. So between 515 apples and 535 apples. And I'm just going to make one other comment here. When I say the true mean, true is just another way of saying for the entire population. So the idea as we go through chapter 7 is that we don't have access to the entire population. So the owner doesn't want to pick apples from every single tree in the orchard. That would seem kind of silly. There'd be no more apples on the trees. So instead, we're looking at a sample, trying to estimate what would be true for the entire orchard.